Hello students, and welcome to another video. I'm your teacher, Mr. Flynn, and today we're going to be talking about periodic trends. Okay, there's going to be a lot of content in this video. It may take you one or two more times to watch this if you're feeling like you're not quite grasping the concept. So make sure to pause. If you need to rewind, go back and watch that section about each of these types of trends. Okay, and if you aren't quite familiar with what effective nuclear charge is, I would go back and watch the previous video. Okay. And a quick summary of that, all of these trends, okay, are directly impacted by effective nuclear charge. So let me summarize again what effective nuclear charge is. Okay, here's the definition for it: is the net positive nuclear charge experienced by an electron in an atom. Okay, so if we look up here, we've got this nucleus that has a positive charge, and it has an influence on these electrons. Now, how great of influence is that? That's what this is measuring. Okay, because we have these core electrons, these blue, that are inside these blue rings, and then our yellow in this outer ring is going to be our valence electrons in this image. Okay, the valence electrons are the ones that interact with their atoms, and they are very far away from the nucleus. Okay, you can think of this as like a crowd at a theater or a concert, right? Everyone wants to be near the front. Everyone wants to be as close as they can, but there are people that are pushing them away from being close to the center. So like electrons in this core, they're being pushed away, but the electrons are wanting to be attracted to the positive nucleus, or for example, near the stage. Okay, so the idea is that as you get further and further away, they feel less and less of a pull because of the charge difference and the charge of the electron versus how large the charge of the nucleus is, and that distance that's between them. Okay, like closer electrons will feel a greater pull toward the nucleus. Okay, so we're talking about the overall effects of how an electron feels that pull toward the nucleus. Okay, and we're going to talk about that trend today. And we talked about this last time, how as you work your way across the periodic table, you'll find that the effective nuclear charge increases because the nucleus is bigger as it works its way across, and they're all overcoming the same amount of core electrons. So aluminum is much bigger than sodium as far as protons, has 2 more protons, but it's overcoming the same 10 core electrons as sodium. So it's better able to hold on to those valence electrons, so it has a higher effective nuclear charge. Okay. Now let's talk about how this relates to the atomic radius, ionization energy, and so forth. Okay. So I wanted to write down this definition. Atomic radius is 1/2 the distance between the nuclei of 2 atoms of the same element. Okay. These elements by themselves, it's hard to measure what their size is. So how we do it, let me draw this out for you. Let me grab, and there it is. It's right here. I'll draw it right here. You can think of 2 atoms when they're next to each other, right? They're spheres. All right, and they have a nucleus in them, and we can measure that distance, and it's 1/2 of that distance between 2 nuclei. Okay, so that's how we determine atomic radius. Okay, that's how we know how large these atoms are. It is used to estimate the size of an atom. Now, let's go through this and unpack what's going on down here. When you first look at the periodic table, you think, oh, lithium, beryllium, you work your way all the way across. The numbers are getting bigger. There's more protons, there's more material. You think, oh yeah, it's getting bigger as I go across from like boron to neon. But if we look at our picture, they actually get smaller. So you see that there? It goes from, I think it's 84 picometers. That's what they're measuring in. Yeah, picometers, all the way to 58 picometers. Okay, it's getting smaller and smaller. All right? And the reason it is because the effective nuclear charge is increasing. The ability for the nucleus to pull in those outer electrons is greater for neon than it is for lithium in that same period. And sodium to argon. All right? And if you look here, it's almost, yeah, there's a large percentage. It went from 166 to 106. It lost about 1/3 of its size from sodium to argon just within these main group elements. And that's because that nucleus is larger and they're all overcoming the same number of core electrons. So the pole is much greater. So that's where this pattern comes from. Okay? So just remember, the atomic radius increases as you go from right to left and from top to bottom. Okay? Because these are all overcoming. They all have one electron in their valence shell, and their ability to pull them in, all right, will increase. The radius will increase as you go down because they all kind of have that same characteristic. They're all pulling at that same rate. Okay, so but they're just larger versions of the one before it. Okay, so the atomic radius will increase as you go down, and then as you work from the right to the left. Okay. All right. There's another image here. If you want to pause and read through this, I'm not going to. All right. This just kind of explains what I just did with that picture. Okay. Now let's talk about what an ion is. All right. You may have heard me talk about it in class, like what an ion is. All right. So I want you to pause the video, and I want you to write down these 3 definitions. Okay. All right. So an ion is an atom or a group of atoms that has a positive or negative charge. All right. So how do they gain and lose charges? Well, they actually gain and lose charges by losing or gaining electrons. Okay. And when an atom loses an electron to form an ion that is positive, we call it a cation. And when an atom gains electrons, it becomes an anion, and it becomes negative. So let's go up here and talk about it in this image. All right. So we have 2 examples here. We have sodium and fluorine. Okay. Sodium has 1 electron in its valence shell, and sodium has a really hard time to holding on to that 1 electron. So it actually wants to just give it away. That's why sodium is considered reactive, because it wants to give electrons away. And when it gives electrons away, all right, it's now more positive. Okay, so if we look at this image, right, we have 11 protons and 11 protons. Our protons stay the same, but our number of electrons changes. Okay, it's losing negativity, so it has now more positivity, so it's going to be more positive. That's why it has a little plus sign at the top here, Na+. All right, this is an ion. All right, and here's some other examples of lithium, sodium, and potassium. They all exist in this first column. They're alkali metals. They share similar properties. They all have 1 electron in their valence shell. They can't hold on to it very well, so they tend to get rid of them. And when they lose electrons, you can assume that they're going to get smaller, right? You can see that they all shrink in size. So as atoms lose electrons, they get smaller. They lose electrons, they get smaller. Okay. Now, on the flip side, fluorine is on the other side of the periodic table. It's all the way over here. Okay. And it's going to want to gain an electron because it wants to have a full shell. All right. If you look at sodium, because it lost 1, does it now have a full shell at the level underneath it? It does. And fluorine wants to have a full shell as well. So in order to get a full shell, it's easier to gain 1 than to lose the 7 that it has in its valence shell. So fluorine will gain an electron and it will get bigger. Okay, so this is pretty straightforward as far as size goes. If it's losing electrons, it gets smaller. If it's gaining electrons, it's getting bigger. And if you think the electrons, if it's gaining an electron, it's gaining more negativity, it's going to be negative. So if you see fluorine has a negative sign next to it, chlorine has a negative sign, and bromine, all right, they all are hanging out on this edge and they want to have a full octet like these noble gases do. All right, we will get into this more and more, and I'll remind you of these concepts, and we'll learn more in depth on them when we get to chapter 3 in the next chapter and how they do chemical bonding. But I want you to remember this. These ones at the end are called the noble gases, all right? And noble gases noble gases already have a full octet. Their outer valence shell is full. They don't want to lose electrons and they don't want to gain electrons. They are content with their allotment in life, just like nobles are. They're given status, they're given riches and all those other things, popularity. They didn't have to work for it. It already was given to them. They are in a state where they are happy, right? That's why helium and neon and argon, they're inert gases. They don't react with anything because they don't need to. They don't want to. But fluorine, chlorine, and bromine, they are all very reactive because they all want to get one to be like nobles. So everyone else in the periodic table has to make changes to their characteristics to become like our noble friends, right? And if you think about this side, lithium, sodium, potassium, they have to lose their electrons so that they can become like neon or argon or helium. They have to lose electrons to get back to a full octet. And the same goes for all these others. Transition metals are a little different, but the main group elements, the S and P block, all of these elements want to gain or lose electrons so they have full octets. All right? So just keep that in mind when we get into chapter 3. And keep that in mind as we talk about this because it's kind of an important idea. All right? Okay, now let's get on to the next trend, ionization energy. Okay, I want you to write this definition down. It is the energy required to remove the outermost electron from the ground state of a gaseous atom. Okay? In short, it's the amount of energy that is required to remove the outermost electron. So if we look here, lithium, sodium, potassium, these alkali metals, they want to get rid of one electron, and they're really ready to get rid of it. They don't want to keep it. They want to get rid of it. Okay? So lithium, sodium, potassium have very low ionization energy because they just want to get rid of it. Okay? While on the other hand, fluorine, chlorine, bromine are halogens on the other side. They really want to gain electrons, not lose them. So it actually requires a little more energy. And that's why the noble gases have the highest, because it takes a lot of energy to remove an electron from helium because it is happy with its arrangement. It doesn't want to give them up. While the ones on the left side of the table want to give them up. They want to be like a noble, so it's easier for them to give one away. Right? And as you work your way across, you'll find that it takes more and more energy to remove these electrons because they don't want to get rid of them by the time they get over to this side of the table. Okay? And you can see the numbers. If we look at lithium to fluorine, all right, they're all in the same period. It goes from 520 kilojoules all the way up to 1600, almost 1700 kilojoules, right? It's dramatically different. It takes a lot more energy to remove an electron. Okay? Now this leads to the next idea of successive ionization energies. So if we look here, we have sodium all the way to argon. Okay, this is period 3 on the periodic table. It runs from the left to the right side, all the way to argon. And you'll see this staircase here. All right, and this is referring to where the, I would say, it hits core electrons. All right, and I'll explain why. So sodium has 1 electron in its valence shell, and it takes 496 kilojoules to remove it. Now, that's the only valence electron it has. Now we get to core electrons, which is 4,562 kilojoules. It goes up by a magnitude of almost 10. Okay? To remove core electrons, it takes a lot of energy. Valence electrons are more easily grabbed and you can pull them off. And you'll notice that as you work your way through. Magnesium has 2 valence electrons, so it's easy to pull the first one off. It's a little more difficult to pull off the second, but once you start touching the core electrons, it goes up. It becomes much more difficult to yank a magnesium core electron away. And that goes all the way down. So for example, by the time we get to, let's say, sulfur, we can nab the first, the second, the third, the fourth, the fifth, the sixth. We can nab those all under 10,000 kilojoules, but when we want to nab that 1 core electron, it's 27,000 kilojoules. It takes a lot of energy to remove that core electron. Okay, so just remember, it's easy to take the valence electrons, but it's much more difficult to take core electrons. All right, and here's a picture describing what I just showed. All right, this black dark ring is resembling just the 1 electron, but then once you get your valence shell's gone, and now it has a full octet, and it likes having that full energy level. It doesn't want to get rid of them. So it takes a lot of energy to pull one of those off. Magnesium has 2. So you pull off the first, you pull off the second, and then by the time you get to that 3rd electron, it's a core electron. It does not want to get rid of it, so it takes a lot of energy to pull that off. Okay? All right. Now let's talk about the 3rd trend, and that's electron affinity. Okay? It is the energy change that happens when an atom gains an electron. Okay? So when electrons join an atom, it releases energy. Okay. Lithium to fluorine, right? We keep going back and forth to the extremes, okay, because these guys all fall in between. But if we look at the extremes, we can see, all right, fluorine really wants to gain another electron. Okay, so when it gains that electron, it's going to release a lot of energy. While lithium likely doesn't want to gain an electron, so it's going to give it away, so it's going to be a lot less. Okay, don't worry about the negatives for now. All right, all you got to think about is the number. If it's bigger, it really wants it. It wants to gain that electron. It's going to release more energy versus on the other side is wanting to give it away. Like beryllium doesn't even want to, it has 0. Okay, it has very low electron affinity. But for the trend, it tends to work its way from the left to the right, all right, and from the bottom up. Okay, all right, there's a few kind of examples here, but as you work your way up, for the most part, electron affinity increases. All right, these are mostly just trends. Okay, and if you want to take it by case basis, you can look at these trend numbers and get what you're looking for. But as we look at the trends, they tend to go up toward this corner. They really want to gain electrons. Okay. All right. Okay. Common charges and representative elements. Now this is kind of a summary of what I've been talking about, and that is atoms want to gain or lose electrons. Right? So if you're on the left side of the table, they are really wanting to get rid of electrons so they can have a full octet. So generally they do that and they form ions. And then the second family or group, okay, the alkali earth metals, they're going to lose 2 electrons because they want to have a full octet. Right? And as you work your way to the other side, they don't want to lose electrons. They'd rather gain electrons to be like their noble gas counterparts. So the halogens are going to want to gain 1, so they're going to have a negative charge, while groups 6 and 5 are going to gain 2 and 3 respectively to get to become like noble gases. All right, so these elements are typically in ion form in nature. They don't exist as oxygen having 8 electrons and 8 protons. Okay, most likely it's going to want to gain protons, so it's not protons, it's going to want to gain electrons, so it's going to have a negative 2 charge. All right. If I want to add anything else. Okay, so when you're thinking of these elements, you got to think of them as having charges because that's what they're going to be like in nature. Also, here's another thing I'm going to say. This side are the givers and they are the takers. All right, these metals tend to be givers, while non-metals tend to be takers. All right, that's how I'll refer to them from time to time. It's like it's taking, they are giving, they're sharing. You know what I'm saying? All right, they're going to form bonds with each other, and we'll talk about that next chapter. All right, so we have the givers and the takers. Now let's connect all the trends. All right, we can see that there's 1, 2, 3, 4, 5 trends that we need to be worried about. Okay, we have non-metallic and metallic character. We talked about that in the very beginning. As you work your way up to this corner to helium, it's going to be non-metallic. And as you work your way down to francium, all the way at the bottom left corner here, they're going to be showing more metallic features. All right, and we've talked about those, metallic and non-metallic. If it's metallic, they're good conductors, while non-metals are not good conductors. They're opposite of each other. Okay, and then inside here we have a little group. All right, I've darkened it on your periodic table so you can recognize it. We call those the metalloids. They kind of exist in between. But if they're going toward this corner, they're going to be more non-metal-like. And if they're going toward this corner, they're going to become more metallic. All right? These tend to be malleable. Their softness depends on where they are on the table, but for the most part, they're malleable. They can be ductile. You can't do that with these elements up here because they're either in a gas form or they're in a powder. All right? So they tend to have opposite characteristics of each other. All right, and then we have atomic radius. Okay, the atomic radius increases when you go from the right to the left. Atoms get smaller as you go to the right. That's because their effective nuclear charge is affecting this. All right. The next was, we'll do electron or ionization energy. Okay, the amount of energy it takes to remove an outer electron. As you work your way from the left to the right, it takes more energy to remove electrons. They don't want to give them away. Okay, and electron affinity is kind of associated with ionization energy in the sense that it wants to gain electrons and it impacts its energy release when it takes in that electron. All right, so keep in mind, these are the 5 trends that I need you to know. You need to understand this chart. And if you don't understand these different parts, go back in my video and watch each of those sections or read the chapter. All right, suggest this will take a little bit of thinking, because some of these things are not quite obvious. Like, you would think that as you work your way across the table that they would get bigger because they have more stuff. That's not the case. They actually get smaller because of that effective nuclear charge. All right, and it goes from 1 all the way to 8. All right. All right, so just become familiar with this image. I think that's it for this chapter. Yep, and then we're on to chemical bonding. Okay, so if you have any questions, please come talk with me. Besides that, we'll see you next time.